Okay, so we're starting chapter 6. We're looking at different polygons. In the last unit, we looked at triangles. This unit, we're going to look at quadrilaterals. Now, the first thing, 6.1, just talks about the sum angle theorems. So if you have a polygon with n sides, then the sum of the interior angles is equal to 180 degrees times n minus 2. Now, let's think about that. We proved in the first unit that a triangle n equals 3 has 180 times 3 minus 2 or 1, or 180. We proved this. We don't need the formula. We proved this. How do we build up? Well, let's do a couple of these, and we'll come up with some inductive reasons to prove this. Well, let's take a look at n equals 4, like any quadrilateral. Okay. Well, before we get to the formula, can we figure out how to find the sum of the angles of a quadrilateral? The answer is yeah. If we draw a diagonal in here, we have two triangles, and that gives us 360 degrees. So we can clearly see that the sum of the angles, the interior angles of a quadrilateral is 180 degrees. I guess we could use this technique for, a pentagon. Here's one technique. If we draw two diagonals in there, we seem to have three triangles. So with a pentagon with 5 sides, if we draw two diagonals, we create 3 triangles, and that's 3 times 180 degrees, right? We can do that with anything. We see that, for example, let's take an octagon, or let's take a pentagon. A hexagon. And so if I start with the vertices 1, 2, 3. So we have. Oh, did I make another? I apologize. So if we use a hexagon, 6 sides. If I pick any vertices, how many diagonals can I draw? Well, I can't draw them to the one next to them, so I have to draw 1, 2, 3. So let's see, 1, 2, 3, which creates 4 triangles, 4 times, so n each sides, 4 triangles, that is 4 times 180, and then that gives us the sum of the angles of a hexagon. Another thing we could do, another way we could look at this is, let's take a look at our pentagon again, okay? And what you could do is you could draw a point in the center of the pentagon. It is the center, and you can draw little triangles outwards, and you can say, okay, Mr. Adler, I have 5 triangles, which is 5 times 180, but then you would recognize that I can't count. I have to get rid of that. I have to get rid of these in the center, and that's minus 2 times 180, and you see that 5 minus 2 times 180. Same thing with the hexagon. You can start with the center and draw out the spokes or the radii, which we're going to see in the area chapter. You say, okay, if a polygon has, can you see that? Yeah, if a polygon has 6 sides, I can create 6 triangles. But I still have to take out this 360. 6 minus 2 times 180. Hence the formula. Okay, next. And the problems just flow from that. The next thing we want to talk about is something called a regular polygon. It's also known as an equilateral or an equal. There's equilateral polygon, all sides are congruent, and an equal angular polygon, all angles are congruent. But we just want to talk about a regular polygon. which is a polygon whose sides and angles are congruent. Now, we're familiar with these. The equilateral triangle. We're going to study this unit, the square. The square is another regular polygon. The sides are all congruent, and the angles are congruent. So, you might say, I might say to you, how do you figure out the sum? So this one of the angles in a regular polygon, and you would say, oh, you know what, Mr. Adler? So the sum, not the sum. So the measurement of one angle in a regular polygon is the sum of all the angles, but we just divide by the sum n. So we know that 180, over here, we know 180 divided by 3 is equal to 60. 360 divided by 4 equals 90. Now, and then you can, what about the others? Let's take a look at the other ones, because this will be interesting, because we want to take a look at this. How about we have a pentagon? What's the sum of one regular, let's say it's a regular pentagon, you say, well, what's the measurement of one of these angles? You go, okay, no problem. 540 divided by 5 equals 108. And in a hexagon, we have, what is this? 720 divided by 6 is 120 degrees. So this is 108. This is 120. Okay. That's part 2 of the unit. The third part of the first chapter of 6 is looking at exterior angles. We want to know what the sum of the exterior angles is. What is the sum of the exterior angles? The sum of the exterior angles of any polygon equals 360 degrees. Now, I want you to think about ways you can prove this on your own, but I'm going to show you a couple of examples. So, let's take a regular triangle with any 3 angles. So, let's say this triangle has 62 and, 85 degrees. Well, I guess my first question to you is, what is the measurement of the third angle? Find x. Well, you say, fine. 85 plus 62 is 147. 180 minus 147 is equal to 33. This is 33. Now, the last part talks about the exterior angle. So, can we see that? Yeah. So, what are the exteriors? Well, what I'm going to do is extend. Okay, let's start with this angle down here. If this angle is 62 degrees, the exterior angle is 118 degrees. If 85 is the interior, its supplement is 95, and if this angle is 33, its supplement is 147. What is the sum of these angles? Okay, 118, 147, 95. Let's see. This is 20, bring up the 2, 3, 7, 6, carry the 1, 360. Let's try another one. How about we try a quadrilateral? How about some weird quadrilateral that looks like this? Yeah, let me make some angles. Let's say this is 105. This is 91. How about this is, 65? And this angle down here is 65 degrees. As I said before, 105, 91, 65. My question to you is first, what is the remaining angle here? And then extend. What are the sum of the exterior angles? So, let's see. So I have 105, 105, 91, 65. And that's let's see, 5 plus 5 plus 1 is 11, carry the 1, 16, carry the 1, 261. We know the sum of the angles of a quadrilateral is 360 degrees, so it's 360 minus 261. That's, well, if it was 260 to 360, it would be 100, but I'm already 1 there, so I only have to go 99. That's cool, 99. So I know the sum of I know the fourth angle. Now, let's add these up. Oh, yeah, it's perfect. Okay, now, so we know the sum of the angles is 360. Extend, 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 extend. What is the supplement of 105? 75. What is the supplement of 99? 81. Oh, sorry. What is the supplement of 65? 115. And what is the supplement of 91? 89. Well, what are these sums? Well, let's see. 75, 81, 89, 115. Let's add these up. Let's see. 5, 10, 20. Bring up the 2. 9, 17, 25, 26, 360. Nice. The sum of the exterior angles of a regular polygon, of any polygon, I apologize, is 360. Now, let's take a look at a faster way to figure this out of regular pentagons. I know that the question is, let's go back to this question. The question I asked you was, what was the measurement of one angle, one interior angle of a regular pentagon? And, you use the formula, 180 times n5 minus 2, you got 540, you divide it by 5, that gave you 108. Now this new method, if you know it's a regular pentagon, you can say, you know what, Mr. Adler? All the sum of the exterior angles, not only is their sum 360, but they're all the same. So 360 divided by 5 equals 72. So if the exterior angle is 72, the interior angle is 108. And so a quick and easy way. Same thing here. We know there's 6 exterior angles and they're all congruent. 360 divided by 6 equals 60. If the exterior angle is 60, the interior angle is 120. Kind of cool. And then we're going to skip the last part about those parallel lines. You can look at it in the book if you want to. The next thing I want to talk about is something I've spoken about. I know I'm going to go to Unit 6 too. You can stop the video now and do the problems in 6.1, or you can keep watching and take notes. The next unit talks about the characteristics of a parallelogram. And so, first of all, we want to define or definition. What's the definition of a parallelogram? A parallelogram is a quadrilateral with 2 opposite parallel sides. It's a quadrilateral whose with 2 pairs of parallel sides. And so you can look at the picture. This is the general picture of the parallelogram. And so the opposite sides are parallel. That's the definition of the parallelogram. Now, from the parallelogram, we can come up with 5. Yeah, we come up with 5 characteristics. First, what do we have? We have a diagonal creates 2 congruent triangles. What's the proof of that? Well, draw in a diagonal. Now, we know that because in the definition we have parallel sides, I'm going to draw the angles 1, 2, 3, 4. So here's our proof. The idea is angle 1 is congruent to angle 3, and angle 2 is congruent to angle 4. So why is this true? Alternate interior angles are congruent. I'm going to label this A, B, C, D. We know that AC is congruent to AC, reflexive, and therefore we just proved by angle side angle, that triangle ABC is congruent to triangle CDA, angle side angle. That's first. Next, opposite sides are congruent. Well, how do we know opposite sides are congruent? Well, it's easy. CBCCC. Or, I'm going to do that. We can see, therefore, from CPCTC. So we know another characteristic of a parallelogram, which you just proved, is the opposite sides. Not only are they parallel, they're congruent. Now, what else can we use with CPCTC? Well, the first thing is we see that angle B is congruent to angle D. And we can see that 1 plus 2 is equal to 3 plus 4. So, first of all, by CPCTC, we know that angle B is congruent to angle D, and by addition postulate, we know that angle A is congruent to angle C. Therefore, characteristic 3, opposite angles are congruent. Now, I'm not going to get into this. Well, what else do we know? Because these lines are parallel, we know from parallel lines that the interior angles on the same side are supplementary. So that means consecutive angles are supplementary. I'm just going to write that down. Consecutive angles are supplementary. So you can visually see that, A plus B equals 180, and B plus C equals 180, and, C plus D equals 180, and D plus A equals 180. That's another characteristic of the parallelogram. And actually, we proved that earlier. The last one, what's the last one? I think I did it before, and I'm not going to, you can prove it on your own. The other thing we can show is that the number 5 is that the diagonals bisect each other. So I'm just going to draw the visual here. We have our parallelogram. I have my diagonals in here. They may or may not be congruent. We're going to see that in the rhombus. The rhombus, in the rhombus they're going to be congruent. In the rectangle, in the rectangle they're going to be congruent, but we're just at, parallelogram level. So we have diagonals, but we don't know anything about them. The only thing we do know, I think I proved it for you a week or so ago, is that the diagonals bisect each other. And so obviously the algebra problems come from that. And that's it. That's the unit. Have fun.